This is my Precalculus course. Today we're going to learn some more complicated counting problems. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We learned how to count in first grade, but as I said, we're going to learn some more complicated counting problems today. And the concepts that we learned today, we're going to use in upper math courses and even this course. To help us count, we're going to use something called the multiplication principle, and rather than showing you an expression or an equation to demonstrate that principle, it's going to be easier just to show you an example. So we're asked to find how many types of sandwiches we can make if we're allowed to choose one type of cheese, one type of bread, and one type of meat from the following menu. And this seems like a pretty difficult problem because there's a lot of different variations of sandwiches that we can make. So how do we do this? How do we count? Well, again, we're going to use what we call the multiplication principle. And that principle is demonstrated here. We're first going to choose the cheese that we want, and we have three options for cheese: American, Swiss, and cheddar. And then we're going to choose the type of bread that we want, and then we're going to choose the type of meat. And what we're going to do is use this tree diagram, if you will. It's kind of a tree on its side, to help us count how many types of variations there are. It's going to be a visual representation for us. So if we choose American cheese and wheat bread and turkey, that would be one option. And if we choose Swiss cheese and white bread and beef, that would be another option. And if we choose Swiss cheese and sourdough and turkey, that would be another option. So you can see that the ends of the branches tell us how many different variations of sandwiches that we can make. These ends here. And so that's how we count when we're presented with a problem like this. We use a tree diagram, and you can see in this case we have exactly 24 different variations of sandwiches. But we don't want to draw a tree diagram every time we do a problem like this. That would take too long. So we use, again, something we call the multiplication principle. If we take the number of options in the first choice, which would be 3, and multiply that by the number of options in the second choice, which is 4, and then multiply that by the number of options in the third choice, which is 2, then we get the number of variations of sandwiches that we can make. So all we have to do is multiply 3 by 4 and then by 2, and we get our answer. So this is the most important principle that we're going to use today. Again, we call it the multiplication principle for counting. So let's do some practice problems. You have 6 different pairs of shoes, 8 different t-shirts, 5 different pairs of pants, and 2 different hats. How many outfit variations are possible? So all we have to do is take the number of options in the first choice, multiply by the number of options in the second choice, and then multiply by the number of options in the third choice, and by the number of options in the fourth choice. And so we get our answer, 480 outfit variations. So there you go. So as you can see, this is really not difficult. Let's try another one. Jill's father took her to the fair. He said that she could take one of her 5 closest friends. She could have cotton candy, either pink or blue, and she would have time to choose one ride: the Ferris wheel, the merry-go-round, the roller coaster, or the bumper cars. How many outcome variations does Jill have for her day at the fair? So we take the number of options for the first choice, which is 5, she's going to choose one of her 5 friends. Then we take the number of options in the second choice, which is a type of cotton candy, pink or blue. There's 2 options. And we multiply that by the number of options she has for rides. So let's count that again. That's the Ferris wheel, the merry-go-round, the roller coaster, or the bumper cars. So that's 4 options for the third choice. And so she has 40 different outcome variations for her day at the fair. So there's 40 different ways that she can spend her day at the fair. And be aware that this phrase, outcome variations, is just one of the types of phrases that you'll see to name the things that we're counting. You might see something like 40 different ways, or 40 variations without the word outcome. There's a lot of different ways we can say that. So let's try one more of these before you try one on your own. You can see that this is pretty easy. So this takes a very difficult problem, a very time-consuming problem, and it helps us to do these problems quickly. The method that we're using, the multiplication principle. So Ken is going to buy a new car, and he has 5 choices to make. How many outcome variations are possible? Well, he has 4 different types of engines that he can choose, and he has 5 different colors that he can choose for the car, 2 different types of upholstery, 2 different types of wheels that he can buy, and 3 different transmissions. So let's multiply. So it looks like we get 240 different outcome variations. For the car that he can buy. So there's a lot of different ways that you can buy this car that he's purchasing. Okay, so I want you to try a problem. Go ahead and attempt number 4, and when you come back, we'll do it together. Okay, we're back. So he can buy an Apple, Samsung, or LG. That's 3 different options for the first choice. He can choose Verizon or T-Mobile. And lastly, he can buy loss insurance, or he can choose not to buy loss insurance. So that's 2 options for the third choice. So he has a total of 12 different outcome variations. So if you got that right, excellent. Go ahead and try number 5, and when you come back, we'll do it together. All right, we're back. So Amy has 6 different drinks that she can choose, 4 different main courses, 5 different side dishes, and 3 different dining scenarios. So if we multiply all these, we get 360 outcome variations. For her meal. So if you got that right, excellent. Go ahead and try number 6, and when you come back, we'll do it together. Okay, we're back. So they have 3 different options for their destination. They can arrive at their destination by plane or on a cruise ship, so that's 2 different options for the third or for the second choice. They can stay in a hotel or with friends. That's 2 different options for the third choice. They can rent a car, a truck, or walk to their destinations. So that's 3 different options for the fourth choice. And lastly, they can bring their dog or they can leave him at home. So that's 2 different options for the 5th choice. So if we multiply all these together, we get 72. 72 outcome variations for how they can spend their vacation. If you got that right, excellent. Okay, so that was the basic multiplication principle. As you can see, it takes a problem that is very difficult. It's a very difficult problem having to count all these ways to do things. But with the multiplication principle, we were able to do these problems really quickly. So the bad news is that it's very difficult to visualize this stuff. You would have to write out this whole tree diagram. The good news is if we use the multiplication principle and understand how it applies to various problems, then counting becomes very, very easy. Well, now we're going to go to a slightly different type of problem. In the previous problems, each choice had different options. For example, our first choice with the sandwich problem was the type of cheese, and there was 3 options. Then we could choose the type of bread. There were 4 options. So choosing cheese and choosing bread, those are totally different options, and there's a different number of options in some cases for each choice. But now we're going to do problems where each choice is taking from the same pool of options. So here's an example. It says choose a 3-letter code when repetition of the letters is allowed. So there's 26 letters in the English alphabet. And so our first choice is going to have 26 options. Now, because we're allowed to have repetition, our second choice is also going to have 26 options. And our third choice is also going to have 26 options. So we're using the same multiplication principle, but the difference with this problem is that we are, again, taking from the same pool of options. And so the numbers are the same, 26, 26, 26. And so our answer is 26 to the 3rd power. So when there are R choices and N options for each choice, the number of outcome variations is N to the R. So that's this here, N to the R. N is 26 and R is 3. So something that's kind of interesting about this is that all permutations are counted in this scenario. So what that means is if you're going to choose A, B, and C, that's different from choosing C, A, B. You can choose the same letters, but you can just rearrange them, and we're counting all of these different permutations. When you're making a 3-letter code, the arrangement of the letters matters. So cab might mean something different from back. Because again, it's a code, it's a 3-letter code, so the arrangement matters. Now, why is it that you're counting the different permutations? Well, you can see with this tree diagram. Again, if you want to understand the concept behind this, we use a tree diagram. You can choose A and then B and then C, or you can choose B and then A and then C. It's the same letters, it's just in a different order. So you're counting, in this case, if you were just using the first 3 letters, you could rearrange them in 6 different ways. So when you look at these 17,576 outcome variations, all of the different orderings of the letters are counted. Now again, there's 26 letters, so we're not just going to use A, B, and C. We could use D, E, F, all the letters of the English alphabet. So again, the bad news is that this is very hard conceptually to understand, because we don't want to have to draw a tree diagram every time we do this. But The good news is, if we understand the context of the problem, we can use the principles that we are learning today, the multiplication principle and this expression here. So let's try some problems. It says a bank customer must choose a 4-digit PIN number. When you get a credit card or a debit card, they're going to ask you to choose a 4-digit PIN number. And each digit can be 0 to 9. Now, some banks may not allow you to choose certain numbers. But in this case, we'll just say that you can choose any of those numbers from 0 to 9. So I could choose 0, 0, 0, 0. Now, realistically, the bank is probably not going to let me choose that number, but let's just say that they would. I can choose 0, 1, 2, 3. Or I can choose 1, 0, 2, 0. Or I can choose 1, 2, 2, 2. So any number from 0 to 9. So how many different outcome variations are there for the customer's PIN? So let's make the first choice. How many options do we have for the first choice? Well, there's 10 options. And how many options do we have for the second choice? Again, 10 options. And the third and the fourth. And that's it. So that's the answer. 10 to the 4th power. So, as you can see, as long as we understand the basic idea here, this is really not that difficult. So, 10 to the 4th power is 10,000. So there's 10,000 different pins that you can choose. We'll say pin numbers. So let's try another one of these problems. RNA is a strand of genetic information made of subunits called nucleotides. Nucleotides are named by the base that they contain: adenine, guanine, cytosine, and uracil. How many 15 nucleotide RNA strands are possible? Now this seems kind of complicated, so let me show you what this is talking about. So in our bodies we use RNA to express DNA, and we use letters in the study of genetics to notate the nucleotides. So we have A, C, U, and G. And G can be repeated, A can be repeated, U can be repeated. We can have any order of these letters. And when you combine these letters on an RNA strand, you have a particular gene. Now, technically in the real world, not every combination would give you a functional gene, but we just want to know how many different strands are possible based on how we can permute the 4 different nucleotides on RNA strands. So, how many options do we have for the first choice? We have to choose 15 nucleotides. How many options do we have? Well, we have 4, because there's 4 nucleotides. There's the adenine nucleotide, the guanine nucleotide, the cytosine, and the uracil. How many options do we have for the next choice? 4. And the next choice, and the next choice, and the next choice. And we just keep going on and on and on. And you don't really have to write all of the numbers. You can just use exponential notation. But I'm going to write all these numbers just so you can see what exactly is happening. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and we get 4 to the 15th power. So again, that is the same thing as n to the r. And 4 to the 15th power is a pretty big number. So we're going to need our calculator for that. 4 to the 15th power is a billion. It's more than a billion different options. So we're going to need to use an arrow. It's 1,073,741,824 strands that are possible, RNA strands. So that was kind of a weird problem. But again, that's just another type of problem where we're counting all the different ways that we can arrange things, arrange letters or numbers. So let's try another one of these. It says nobody knows the dates of Kyle, Lauren, or Eddie's birthdays. How many possible outcome variations are there for the dates? So let's choose the date that Kyle's birthday is going to be on. How many different options do we have? Well, there's a finite number of options. There's only 365 days in a year, so we have 365 options. Now let's choose Lauren's birthday. How many options do we have? Well, we're choosing from the same pool of things. So it's the same number, just like we had the same numbers up here. 10, 4, now we have 365. And notice that we're multiplying by the same number over and over and over again. And now we're going to choose Eddie's birthday, so that's 365. And again, we don't know what their birthdays are. We're just determining the possible number of options. And they could all have the same birthday. That's counted in this math that we're doing now. So 365 to the third power is equal to 48,627,125 dates. And we should probably say outcome variation. That would probably be more accurate. Okay, so it's very easy to get lost with this type of math. It's very easy to get confused. So you have to understand the context of what we're doing. In the previous problems, we had choices, and each choice had very different options. But now we're doing problems where we have choices that all have the same options. So we're multiplying by the same number over and over again. And I want you to try number 10. And when you come back, we'll do it together. Okay, we're back. So there are 28 letters in the Arabic alphabet. How many ways can 5 letters be permuted if repetition is allowed? So we have 28 options for the first letter, 28 options for the second, and the third, and the fourth, and the fifth. Because we're going to choose 5 letters. So we have 28 to the 5th power. And don't be afraid to use your calculator. 28 to the 5th power is 17,210,368. So let's see if we can scrunch that in a little bit. It says how many ways. So instead of outcome variations, we can just write ways if you'd like. Again, there's a lot of different ways to name the things that we're counting. It's not really that important. What's important is knowing how to do the math. So I want you to take a picture of these problems and try number 11, and when you come back, we'll do it together. All right, we're back. So how many options do we have for the first choice? Well, computers, they use ones and zeros, so there's only 2 options for the first choice. And how many options do we have for the second choice? Well, you only have a 1 or a 0 to choose from. So each choice has 2 options. And it would be kind of hard to write all this out, so we can just say we can say 2 to the 29th power. And we're going to use the calculator to figure that out. So 2 to the 29th power is equal to 536,870,912 programs. That's just one name that you can use for the things that we're counting. So if you didn't call them programs, that's okay. That's what I would choose to call these different options. But again, not every combination is going to create a functional program. We're just concerned about the different ways we can arrange the ones and zeros. So if you got that right, excellent. Go ahead and try number 12, and when you come back, we'll do it together. Okay, we're back. So we have 20 different amino acids that we can choose for each, or 20 different options we can choose for each amino acid. And we're creating a strand, a polypeptide strand that has 12 amino acids. So 3, 4, 5, 6, 7, 8, and we don't really have to keep writing all these down. So we can just say 20 to the 12th power. And 20 to the 12th power looks like 4 quadrillion. So 4 quadrillion, 96 trillion, and we have 1, 2, 3, 4 groupings of 3 zeros. So if you weren't able to name that number, that's okay, but this is 1,000, million, billion, trillion, and quadrillion. So 4 quadrillion, 96 trillion different strands are possible. So there's a lot of different amino acids. So that's why that number was so big. If you got that right, good job. Okay, so in order to do the next problems, we're going to have to learn something called factorial notation, and you have a representation of that here. But it's much easier to just show an example problem. So this is called 4 factorial. We put that little exclamation point there, and we call it the factorial symbol. And what this means is we're going to take that number and multiply it by the next lowest positive integer, and the next lowest, and the next lowest, until we get to 1, and then we have our answer. 4 factorial is 24 by definition. So that's what the factorial symbol means, and we use this symbol to help us to write things in a compact form. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So you can see that this is very easy. But having to multiply all these numbers becomes very tedious. So we don't want to do this if we don't have to. Now, if you have a graphing calculator, it's most certainly going to have a factorial symbol. And all graphing calculators are different, and even if I could tell you how to find the symbol in your calculator, it would take too long to show how to do that for every single calculator. So I'm just going to demonstrate this on a TI-84. Now, if you have a scientific calculator, remember, you need to have a graphing calculator by this point. Your scientific calculator probably has that symbol, but you're going to have to figure out how to find it. So what you're going to do in the TI-84 is you're going to press the 7 button. So press number 7, and then you're going to push the math button at the upper left, and then you're going to use the arrow buttons, the up, down, left, right arrow buttons. Press the right arrow button until you go to PRB, probability. You should see RAND, NPR, NCR, and then an exclamation point for number 4. Use the down arrow button and go to the exclamation point at number 4, and then press enter. Now on the screen you should see 7 factorial, this symbol here. So press enter, and it gives you the answer, 5,040. So that is defined as 7 factorial. So that's how you do these calculations faster. So I'm going to do the same thing. I'm going to write it out first just so we know what we're doing. But I don't want to multiply all these in my head. So I'm going to press 8, the math button at the upper left. Then I'm going to use the right arrow key to go to probability. And then I'm going to go down to the exclamation point and press enter. And I see 8 factorial on my screen, and I'm going to press enter. And we have 40,320. That is the value of 8 factorial. So I want you to try number 16. And be aware that I don't know if every TI-84 is the same, so if your TI-84 is a little different than mine, don't be concerned. You can always go to the internet to try to figure out how to use how to call up that factorial symbol. So try number 16. When you come back, we'll do it together. Okay, we're back. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So if we do that on our calculators, we get 720. Now you could probably do that in your head, but you can also do it on your calculator. Now, number 17 you can definitely do in your head, so try number 17 without the calculator, and when you come back, we'll do it together. Okay, we're back. So that's 3 times 2 times 1, which is just 6, so that one was easy. But number 10, you're probably going to need your calculator, so try number 10, and when you come back, we'll do it together. Okay, we're back. So we got, I'm going to go ahead and just write this out just so we can see exactly what's going on. I don't think you really need me to write it out for you at this point, but at least we'll have something to write on the page. And I got a very big number, 3,628,800. So if you got that answer, excellent. Okay, so we're going to use that factorial notation, and we're actually really not going to have to use it today, but we're just going to need to know what it means. So we're going to do a different type of problem now. It's very similar to the previous problems that we did. The first problems that we did, we had choices to make, and each choice had a different number of options. At least they had options that were completely different. Then we went to another type of problem where we had choices to make, but each choice had the same number of options. Well, now we're going to the situation where we have a certain number of choices to make, but the options that we have are going to diminish as we make our choices. And the reason for that is that an option cannot be used more than once. So it's better to do an example problem rather than to try to give the general idea. The Danish alphabet has 29 letters. How many different 6-letter permutations are possible if no letter can be used more than once? So what's different about this problem is that no letter can be used more than once. So if you choose a letter from the 29 different options, then your second choice is not going to have 29 options. It's going to have 28 options. All right? Then the third choice is going to have 27, 26, 25, 24. Now, it's a 6-letter permutations is what we're calculating. How many different 6-letter permutations are possible? So where does the 6 come from? 1, 2, 3, 4, 5, 6. So we're multiplying 6 numbers. And if you multiply these numbers, we get 342,014,400 different permutations. And we can actually write permutations there. Now, as you can see, this gets kind of difficult, so we can do this in our calculator. And the symbols that we use in our calculator are these symbols. Now, the Texas Instruments TI-84 uses this symbol. And we already saw that symbol. So let me show you how to do this in your calculator. So in your TI-84, enter the number 29 and then push the math button at the upper left just like we did before. Use the right arrow key to go to PRB, probability, and then go down to number 2 where it says NPR. Then press enter. Then enter the number 6. So what you should see on your screen is 29 NPR 6. And then press enter. And you should get 342,014,400 permutations. So that's how we do these typical types of problems. Again, the difference is that no letter can be used more than once. So we're choosing from the same pool of things. We have the same options. The only difference is that each time we come up with a number, we have one less option because we're not allowed to have repetition. Now, you see this symbol up here. That's where we need our factorial symbology. So this is a very complicated expression, but what it means is to calculate these numbers. So let me show you what that means. So n in this case is 29. And 29 minus 6 is n minus r factorial. 29 minus 6 is n minus r up here. And what this means is that we're going to calculate 29 factorial in the numerator, but that would go all the way to 1. And in the denominator, we're going to calculate 29 minus 6 factorial, which is 23 factorial. And 23 factorial is 23 times 22 times 21 times 20, so on and so forth. And so when you get to 23, and I guess I'll write that out here so you can see what's happening. This is very complicated notation. You don't really have to know this notation for today, but you are going to see it eventually. So we're going to get to 23 and just keep going on until we get to 1. But the problem is we don't want to keep going. You see, we want to stop at 24, so how do we do that? Well, we do it by dividing out all the terms that we don't want. So we don't want this string here, 23 all the way to 1. We want to cancel that out, you see. So what we do is we calculate 23 factorial in the denominator, and the yellow parts cancel out, so you're left with the blue part, which is what we want. So this notation up here is very confusing. It looks very confusing, but all you're doing is just showing mathematically how to do these problems when repetition is not allowed. So you don't really have to think about this notation when you do these problems. That's just a way to mathematically express how we would do this. If you want to do the actual calculation yourself without a calculator, you could just write this expression. But if you wanted to write a mathematical expression, you would need the factorial notation. So let's try some practice problems. So there are 27 letters in the Spanish alphabet, and before we continue, I just want to recap what we've done because it's very easy to get lost with all this math. In the first problems that we did, we had choices to make, and each choice had totally different options: cheese, bread, meat, right? And sometimes there were a different number of options for each choice. In the second type of problems that we did, we had choices to make, but each choice had the same options and the same number of options. And in that case, repetition was allowed. In the problems that we're doing now, we have choices to make, and we're choosing from the same options, but repetition is not allowed. And so the number is not going to be the same. It's going to be one less each time. So let's try a problem here. There are 27 letters in the Spanish alphabet. How many outcome variations are there for a 4-letter code if no letter can be used more than once? So we have 4 choices to make. The first choice is our first letter. And notice the difference with this problem is no letter can be used more than once. That's what's different. So when we choose the second letter, we don't have 27 options. We only have 26. Then the third letter, and then the fourth letter. And we're done. That's it. So all we have to do is calculate this. Now, there's 2 ways to do this. One way is you could just enter it into the calculator as you see here. But I want you to get used to these calculations on your TI-84 or whatever calculator you're using. So what we want to do is enter the number 27, then push the math button at the upper left, then use the right arrow key to go to probability, go down to number 2, NPR, enter, press the enter button, and then enter 4 on the calculators. So you should see 27, NPR, and then 4. And then press enter, and you should get 421,000. Now I want you to use whatever notation that you want to use, but I'm going to show you both types of notation. So one type is P27, 4. But the type of notation we're using is 27P4. And the way that we write it here is a little different than the way the calculator writes it, just because the calculator, I don't know, the Texas Instruments engineers decided to write that a little different. but we should get 421,200 different codes, and we can just write codes. Okay, so let's try another one of these problems, and be aware that you're not allowed repetition. So if you choose A, B, C, I believe the Spanish alphabet is pretty much the same as the English alphabet. So if you choose A, B, C, that's allowed, but you're not allowed to choose AAA or AAB or ABB because you have repetition. You can't use a letter more than once. So that's what's different about these problems. In the previous type of problem that we did, we would multiply 27 by 27 by 27 by 27. That's when you're actually allowed repetition, but you're not allowed repetition in this case. Now, it's important to understand that you are counting permutations. So if you choose ABC, that's okay. You can also choose CBA or BAC. So the permutations are counted. It's just that there's no repetition allowed. So again, I know that this is very confusing to have to keep track of all these, but the good news is today in class we're only covering 4 scenarios. So the first scenario is where we had a number of choices to make and the options were different for each choice. The second scenario is where we're making choices and each choice has the same number of options and repetition and permutations are allowed. The third situation, which we're doing now, is when you have choices to make and you're not allowed repetition, but you're still counting the permutations of the letters that you are allowed to use. So let's do another problem. There are 20 different types of amino acids used by biological organisms in nature. Amino acids are connected in strands called polypeptides. How many polypeptide variations are possible for a strand that has 9 amino acids if, and here's where things are different, if no amino acid is used more than once. Okay, that's what makes this different. We have 20 different options for the first choice, and we're choosing 9 amino acids, and this can also be written as 20P9. So what this is 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 amino acids that we're choosing. So we have 20 options for the first choice, but we're not allowed to use an amino acid more than once. So because we chose our first amino acid, we're only allowed 19 for the second choice and 18 for the third choice. So we're using the multiplication principle, but we're understanding that we cannot have repetition. And although we cannot have repetition, we're still counting the number of permutations of the amino acids that we are going to use. So I know that this seems like a lot to take in, but again, there's only 4 scenarios that we're going to be covering today. So in your calculator, we'll enter 20, the math button, right arrow key, down to NPR, enter, and then enter 9. So we should have 20 NPR 9. 20 NPR 9. Press enter, and we have a very, very large number. So the TI-84 is most likely going to give you the number in scientific notation because it's set to give you very, very large numbers in scientific notation. So if you want to use the scientific notation, you can write 6.09493248 times 10 to the 10th power. strands. So that's how many different strands are possible. Now, I want to stay away from scientific notation, so I'm just going to write the whole number out. Notice it says E10 at the very end, at the very right, it says E10. E10 means times 10 to the 10th power. The E is the 10, and the 10 at the very far right is the exponent. So if you multiply by 10 to the 10th, that means you move the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to have the same number, just with 2 zeros there. And so I'd prefer to go ahead and write the actual number. But if you want to use scientific notation, that's fine. That's easier because that's what the TI-84 gave us. But if you're using an iPhone, you should get the whole number. So 60,949,324,800 strands are possible. Okay, so let's try another one of these problems. Leonard will give one card to each of his 5 children. He's using a deck with 52 distinct cards. So distinct means every card is different. All 52 cards are different in some way. How many outcome variations are possible? Now, notice that he's giving these cards to his 5 children. Now, his 5 children are all different. So let's say that Cecilia gets the ace of diamonds. That's a different scenario where Cecilia gets the 8 of clubs. So if Cecilia gets the ace of diamonds and Mark gets the ace of clubs, that's different from Mark getting the ace of diamonds and Cecilia getting the 8 of clubs. So again, this is a problem where we have to choose what card we're going to give to the first person. So it's going to be P 52, 5, also written as 52P5. We're going to choose which card to give to the first child. There's 52 options for the first choice, but once we give the first card to the first child, we don't have 52 options for the next card. We only have 51 because we're not allowed to use a card more than once. So then we have the third child and the fourth child and the fifth child. And that's it. So whatever that number ends up being, that's our answer. Now again, it's easier to do this in your calculator, so enter 52, the math button at the upper left, right arrow button, to the PRB, go down to NPR, enter, and then press 5, and you have your answer. So that's going to be 311,875,200 outcome variations. So there you go. Now again, at this point, you might feel yourself becoming distressed. You might think, I don't know if I can remember all this. I don't know if I can conceptualize all of this. I don't know exactly what's going on here. And that's normal. So how do you find your way out of that? Here's how. You understand that we're only covering 4 scenarios here. If you can understand how to use the math in these 4 scenarios and how to recognize the 4 scenarios, then it's going to be easy. The problem is each problem that we're doing is different. And so that's the hardest part, is understanding when to use each scenario. And that does take some time. So if you're a little confused by this, that's completely normal. But again, it's only 4 scenarios. So I want you to take a picture of this page here, and I want you to try number 22. When you come back, we'll do it together. Okay, we're back. So we're going to choose a 4-digit PIN number, but no number can be used more than once. So that's what's different about this problem. No number can be used more than once. So how many options do we have? Well, first let's write the notation here. So how many options do we have for the first PIN number? Well, we have 10. But once we've chosen that first PIN number, we're not allowed to use that same number. So we don't have the same number of options for the second choice. We have now 1 less. And then again and again, and we're done. Now, where does the 4 come in? We're supposed to choose a 4-digit. I don't see a 4 here. Well, 4 is 1, 2, 3, 4. So we're choosing 4 things, and we have 10 options for the first choice, 9 for the second, 8 for the third, and 7 for the fourth. So again, we can go to the calculator, press the 10, enter 10, press the math button at the upper left, use the right arrow key to go to PRB, use the down arrow key to go to NPR number 2, and then enter number 4. So what you should see is 10 NPR 4. And if you press enter, you should get 5,040 outcome variations. So there you go. If you got that one right, good. If you had a little trouble with that, that's okay. These problems are very, very intimidating. So if you had a little trouble, that's okay. It takes a while to get used to these problems. Okay, so I want you to try number 23. When you come back, we'll do it together. Okay, we're back. How many 5-letter permutations are possible if a letter cannot be used more than once? So this assumes that we're talking about the English alphabet. So we're going to write P 26, 5, which is the same thing as 26P5. And that's going to be 26. We have 26 options for the first letter, but we only have 25 for the second letter because we're not allowed to use a letter more than once. And we have the 4th option and then the 5th option, or the 4th choice and the 5th choice. You have to be careful about how we use words here. So we have 26 options for the first choice, 25 for the second choice, 24 for the third choice, and so on and so forth. So again, enter 26 in your calculator in your TI-84, push the math button at the upper left, then use the right arrow key to go to the PRB screen, and then push the down arrow key to go to NPR, and then you want to enter 5, and then press the enter button. So you should have 26 NPR 5 entered, and when you press the enter button, we should get 7,893,000, that is 600 permutations. So if you got that one right, excellent. Okay, so try number 24, and when you come back, we'll do it together. Okay, we're back. So we had a problem like this, and we were allowed repetition in the first problem that we did, so we calculated like so. But now we're told that none of their birthdays fall on the same day. So once you choose the number of options, once you make your first choice, you can't have Jeff or Marla's birthday fall on the same day. So we don't have 365 options for the second choice. We have 364 options. And for the third choice, we have 363 options. So this is P 365, comma 3, which is also written as 365 P3. So again, go to the calculator, enter 365, the math button at the upper left, right arrow key to PRB, go down to number 2, enter NPR, and then enter 3, and then press enter, and we get 48 million, and I'm going to write that down here, 48,228,180 outcome scenarios, or outcome variations, however you want to name the things that we're counting. So if you got that one right, excellent. Now again, if you're having trouble with this, that's okay. That's perfectly normal. These problems are very intimidating. So the most important thing today is just to get used to how these problems work. Okay, so let's try this next problem together. There are 10 women auditioning for a play that has 6 distinct female characters. How many outcome variations are possible for the female cast if an actor is not allowed to play more than one character? So this is going to be P10, 6, or 10P6, however you want to notate it. And we're going to have 10 options of women for the first female character, and then we have 9 options for the second female character, because we already chose a woman for the first character. And understand that, again, no actress is allowed to play more than one part. So once we choose an actress for one part, we can't choose her for the next part. So then we have the third woman, and the fourth, and the fifth, and the sixth, and so on and so forth. So 1, 2, 3, 4, 5, 6, and that is the answer. So again, we're using the multiplication principle. We're not allowed to have repetition, but we are counting permutations, because let's say that the first actress is going to play a character named Wendy, and the next actress is going to play a character named Charlotte. Well, we can switch. This actress can play Wendy, and this actress can play Charlotte. So that's a different scenario. We're counting all of those different permutations. So we don't allow repetition, but we are counting permutations. So in the calculator, we're going to enter 10, and then math button, right arrow key to the PRB, down to number 2, NPR, and enter the number 6, and then enter, and we get 151,000. 151,200 different outcome variations. or we could say casts. That's how many different casts there are that are possible. Alright, let's try another one of these problems. 4 musicians must be chosen to play in a rock band. There will be a lead guitarist, a bass player, a singer, and a drummer. If there are 17 musicians auditioning and each one is capable of playing any instrument, that's not realistic, but let's just say that everyone is capable of playing all the instruments, how many different outcome variations are possible? And note, a band where Andy is the lead guitarist and Bill plays bass is different from a band where Bill is the lead guitarist and Andy plays bass. So we're not allowed repetition because we're told to assume that only one musician is allowed to sing. So we can't have a musician be a singer and a bass player. We're going to choose 4 different musicians with different parts. So no repetition, and but we are going to count the permutations, because again, a band where Andy is the lead guitarist and Bill plays bass is different from a band where Bill's the lead guitarist and Andy plays bass. So I know that this is confusing, but we're going to choose the first musician. How many choices do we have? Well, we have 17 different choices. Now that we chose that musician, and let's say we're choosing the lead guitarist, so we choose our lead guitarist, then how many options do we have for the bass player? Well, we already chose one musician, so we only have 16 left. So 16 options, and then 15, and then 14. So that is the same calculation that we've been doing. So we'll enter that into the calculator, and we get 57,000 different options. 57,120. We'll just say bands are possible. So again, this counts all the different permutations. So if Andy is the lead guitarist and Bill is the bass player and Jeff is the drummer and Alan is the singer, you can then take those musicians and rearrange them and have them play different parts. That would be a different band according to this problem. We're counting all the different permutations, but we're not allowed repetition. If Andy is chosen for lead guitar, he can't play bass at the same time, right? Or if he's chosen to sing, he can't play bass at the same time, even though that does happen. In this problem, it says, assume that only one musician is allowed to sing. So I want you to take a picture of number 25 and number 26. Well, you can just keep that in the window. Try number 27. When you come back, we'll do it together. Okay, we're back. So this is going to be P15, 9, or 15P9, however you want to write it. You don't have to write both of these notations. You can just choose one. And I would choose this one if I were you, because that's what your calculator uses. So notice that these are distinct positions. So how many different players do we have for the first position? Well, there's 15, and then 14 left for the second position that we're going to choose, and so on and so forth. So there's 9 total positions. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 15 options that we can choose for the first position. Once we choose that player, we only have 14 players left for the second position, and so on and so forth. So we'll enter this into the calculator. Enter 15, then the math button at the upper left, right arrow key to PRB, go down to number 2 NPR, press enter, then enter 9, and we have a lot of different options. So it looks like that's going to be 1,816,214,400. We can just say teams. So if you got that one right, excellent. Go ahead and try number 28, and when you come back, we'll do it together. Okay, we're back. So there's 11 employees that we can choose from. So in the first position, we're going to choose 11 people, and we're going to choose from 11 people. We're going to choose 1 out of 11 people, and then the second option, we only have 10 people left to choose from, and the third, we have 9 people. So that's going to be 990 outcome variations, or we could say teams. So again, we're not allowing one person to have multiple positions. No repetition is allowed, but we are allowing for permutations, because a team where Douglas is the president and Marvin is the vice president is different from a team where Marvin is the president and Douglas is the vice president. That's a different team, so we're counting all those different permutations. Okay, so let's try another one here. How many different ways can 6 people be lined up? Believe it or not, this is actually just the same type of problem that we've been doing. So how many people do we have to choose from? How many options for the first choice? We're going to line people up. We're going to choose the first person. Well, we have 6 different options for the first person, because there's 6 people total. So think of this as slots. So we have the first slot, the first place where a person is going to stand. You have 6 different options to put that person there. Once you choose a person for the first place to stand, then you have to choose another person. You can't choose the same person twice. So there's going to be only 5 people to choose from for the next place to stand, and so on and so forth. So the answer is actually just 6 factorial. So this is just an example where you have 6 things, 6 choices to make, and you have 6 options for the choices, but you're not allowed repetition. But this does count permutations. So if you line up 6 people, whatever this number is, that counts all the different ways that you can rearrange the people. But you cannot use the same person for 2 places to stand. That doesn't work, right? So we're going to use our factorial notation. We're going to write, enter the number 6 in the calculator, push the math button at the upper right, push the right arrow key to PRB, and then go down to number 4, enter, and you should see 6 factorial. Then press enter, and we get 720. So here's an example where we use the factorial button. And we can just say ways. Okay. So let's do another one of these problems. Amanda will put 5 pies on the windowsill to allow them to cool. One is apple, another is lemon, another is blueberry, another is cherry, and the last is pumpkin. How many ways can she line them up? So this is another problem that is P5 5, comma 5, 5p5, how many pies does she can she choose from for the first place on the window seal? So think of this as places on the window seal. She has 5 different options for the first place. Once she chooses her first pie, she only has 4 different pies left to choose for the second place on the window seal, and 3 and 2 and 1. So all we have to do is calculate 5 factorial. And by the way, I'm going to go ahead and write the factorial just so you can see how to calculate that up here. So all of that is equal to 6 factorial, just like this is equal to 5 factorial. So enter 5, push the math button at the upper right, use the right arrow key to go to PRB, probability, go down to number 4, which is a factorial, press enter, and then you should see 5 factorial on your calculator. Press enter, and we get 120. 120 ways that she can line up those 5 pies on the window seal. Okay, so I want you to try number 31. And when you come back, we'll do it together. Okay, we're back. How many different ways can 9 people be lined up? Well, that's just P9, comma 9, which is 9P9, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is the same thing as 9 factorial. And press 9, press the math button at the upper left, right arrow key to probability, go down to number 4, factorial. You should see 9 exclamation point in your calculator. Press enter, and we get, I'll put this down here. Well, I actually don't have enough room for that. We get 362,880 ways. So there you go. I'm going to move this up a little bit, move it over. So if you got that answer, excellent. So go ahead and try number 32. And when you come back, we'll do it together. Okay, we're back. So he has 4 different hats to choose from. For the first day. Let's say the first day is going to be Monday. So he has 4 different hats, but he's not going to wear the same hat again. You're not allowed repetition. So he only has 3 options for Tuesday, and 2 for Wednesday, and 1 option for Thursday. So the answer is simply 4 factorial, which is 24 outcome variations. So if you got that right, excellent. Now this does count the permutations. So if he wears, for example, his green hat on Monday and then his blue hat on Tuesday, that's different. That's a different situation if he wears his blue hat on Monday and his green hat on Tuesday. So this is counting all of those different permutations, but it's not allowing repetition. So he can't choose the blue hat for Monday and the blue hat for Tuesday again. So if you got that right, excellent. Okay, so now we're going into the 4th scenario. We've done 3 scenarios. The first scenario is when you have choices to make, and each choice is totally different. For example, the type of cheese for your sandwich, the type of bread, the type of meat. And the number of options is not always the same. The second scenario is when we had a number of choices to make, and each choice had the same number of options, and we were allowed repetition. In the first scenario, we obviously were not allowed repetition because there's no such thing as repetition. You choose your cheese, and then you can't choose your cheese again on the second choice. You have to choose the bread. But in the second scenario, we were allowed repetition. In the third scenario, and by the way, the second scenario, we counted the permutations. In the first scenario, there are no permutations. Eating American cheese and then wheat bread is the same thing as eating wheat bread and American cheese. If you flip them around, it doesn't do anything. So there's no permutations we had to worry about in the first scenario. In the second scenario, we were counting permutations and we had repetition. But in the third scenario we did previously, we were taking we had choices to make, and our options were the same options, just like the second scenario. But in the third scenario, we were not allowed repetition. But we did count the permutations. So this is a lot of stuff that I have to take in. Now we're going to the fourth scenario. And I know what you're thinking. You're thinking, how in the world am I ever going to remember all these scenarios? Well, the good news is there's only four. There's only four scenarios that you have to remember. So this is the fourth scenario. In this scenario, we have choices to make, and we're going to choose from the same pool of choices, just like we did in the previous two scenarios, scenario 2 and scenario 3. And we're not going to be allowed repetition, just like the previous scenario. But what's different about this is we're not going to count the permutations. We're not counting permutations. So let me give you an example. The Danish alphabet has 29 letters. How many different 6-letter combinations are possible if no letter can be used more than once? So we're not allowed repetition because no letter can be used more than once. But what is different about this? Notice we're not asking for permutations. We're asking for you to count combinations. That's different from a permutation. So, for example, I don't know what the Danish alphabet looks like, but let's use the English alphabet. Let's say you choose A, B, C, D, E, F. So we chose 6 letters. But what if you don't care about the orders of the letters? What if you switch it around so it's F, E, D, C, B, A? Or A, C, B, E, D, F? These are different permutations. But when you're counting combinations, we don't care about the permutations. We're not counting those. So for every grouping, and by the way, combinations are also called groups. For every group of letters, there's a certain number of permutations that we have to divide out because we don't care about those. When you divide, you make the number smaller. So we learned that in the previous problems, if you want to figure out how many ways you can line something up, that's basically determining how many permutations there are. So if you have 6 things and you want to figure out how many ways you can permute them, you just find 6 factorial. That's the different permutations. But we don't care about those permutations. So we're counting 6 factorial more things than we want to count. So for every combination of letters, there's 6 factorial 6 factorial permutations. So we have some number, we're counting the number of groups, but then we're multiplying that by 6 factorial. So that's this blue part here. What we're doing is we're dividing out the 6 factorial because we don't want that. We don't care about the permutations. So we're dividing it out. We're dividing all this out, and we're left with the number of combinations, which is going to be a lot less because we don't care about the permutations. Now, I know what you're thinking. You're thinking, I don't get this. This is pretty complicated. And you know what? You're right. It is complicated. But as long as you know the context of what you're doing and how to use the math, the counting is going to be very easy. Are these problems intuitive? Are they simple problems? No, they're not simple problems at all. But all you have to do is know what exactly we're counting, and then you can rely on your multiplication principle and the concepts that we learned previously. So what we're doing is the same exact thing that we did before. We're not allowed repetition, so we choose one letter, 29 options. Then we have 28 options because we're not allowed repetition. Then 27, 26. So we have 1, 2, 3, 4, 5, 6 letters. So there's 6 letters. But we don't care about the permutations of the letters. We're just counting groupings, combinations, not permutations. So we divide by the number of ways that you can permute any group of letters. And you get this number here. The good news is you don't have to do this. Your calculator has a button for that also. Now notice that we have this expression here. This expression is exactly the same as the expression that we had for permutations without repetition. Same expression. The only difference is now we're going to divide by r factorial, because for every group of things we have, in this case, 6 factorial permutations, r factorial permutations. So we have to divide by that. So this part was the same. It's the same as the expression for the previous thing that we did, but now we just have an r factorial because we're dividing. We don't care about the permutations. So again, I know that this is very intimidating, but with some practice, you'll start to get a feel for when to use the various equations that we're using. So 12 scientists must be chosen to study the coral reef in Australia. If there are 17 scientists willing to go, how many possible outcome variations are there? So notice that we're not told that there's going to be particular positions for the scientists, even though in reality you would have a leader, a scientist who's the leader, and then you would have the second in command guy, and you'd have different people doing different jobs. We're not told about that here. We're just told that you're going to choose 12 scientists, so we don't care about any kind of permutations of the scientists. So now we're going to write C for combination. P stands for permutations, because we're counting permutations in the previous problems, but now we're not counting permutations for it. So we write C combinations, and actually that should be 17. 17 comma 12. So 17C12. And what we're doing is we have 17 options for the first scientist. Then once we choose the first scientist, we only have 16 for the second, and so on and so forth. So we need 12. So that's 1, 2, 3, 4, 5, 6, 7, 8. And we need to multiply 4 more times. So I think we got enough there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because there's 12 scientists that we're choosing. So that's a big number to calculate. So luckily our TI-84 can do this for us. So we're going to enter 17, then we're going to push the math button at the upper right, then push the right arrow key to get to PRB, probability, then go down to number 3. Instead of number 2, NPR, we're going to number 3, NCR. Press enter, and then enter 12, and then press the enter button, and we have 6,188 possible teams. I'm just going to say teams. So again, we don't care about the permutations. If we choose 12 scientists, we're not going to count the orders that we can rearrange those 12 scientists. We're counting those 12 scientists as one group. Then we're finding another grouping. So you could take one of the scientists out and replace them with somebody else. That would be a second group. And so on and so forth. So here's another example. There are 10 cats at the pound that need to be rescued. Abby has a farm and she'll pick 3 of these cats to catch mice. How many outcome variations are possible? So this is going to be C10, comma 3. And so the reason we don't care about the permutations is because let's say that she chooses Marvin is the name of the first cat. Then she chooses Molly for the second cat. And then she chooses Margie for the third cat. If you rearrange the cats, let's say she chose Margie for the first cat and Marvin for the last cat, does that change the outcome? No, it's the same group. So we're calculating groups. We're not calculating the permutations of the cats. That doesn't make any sense. So we have 10 options for the first cat, 9 for the second, 8 for the third, and 7. Actually, no, we're only choosing 3 cats. But this counts the permutations of the cats. We don't want to count the permutations. So we're going to divide by the number of ways that you can permute the cats, because we're counting, each group has 3 factorial ways that you can permute the cats. You can order them in 6 different ways. Remember, we learned that if you want to line up 3 people, there's 3 factorial ways that you can line up those people. So that was one of the types of problems that we did. So you're counting way too many things because you don't want permutations. So let's go to the calculator and enter 10, and then the math button, right arrow key to PRB, go down to number 3, NCR, and then enter 3. So you should see this in your calculator. And when you press enter, we get 120. 120 outcome variations. Okay, so let's try one more of these. There are 32 students in a classroom. If the students are instructed to form groups of 6 people, how many ways can one group be formed? So this is C32, 6, or 32C6. We have 32 different options for the first person that we're going to choose, then 31, then 30, then 29, then 28, then 27. So 1, 2, 3, 4, 5, 6. But that counts the ways that the students can be permuted. If you have Marvin, Margie, Mavis, and Bill, and Alan, you don't care about the different ways. Was that 6? I don't remember if that was 6. But you don't care about the number of ways you can rearrange these people once you choose them, because they're all the same group. It doesn't matter how you permute them, because we're not choosing leadership for the group or different jobs for the group. In that case, you would care about how you could permute them. So we're going to divide by 6 factorial. And we're going to enter that into our calculators. 32, the math button, go to probability down to NCR, and then 6, and then we get 906,192 ways for one group to be chosen from 32 students, one group of 6. So I want you to try number 36, and when you come back, we'll do it together. Okay, we're back. So this is going to be C27-4 or 27C4, however you want to say it. And we have 27 options for the first letter, and then 26 for the second letter, because we're not allowed repetition, and then 25, and then 24. But this counts the number of permutations. We don't care about the permutations. It says how many combinations. It doesn't ask how many permutations. It asks combinations. So for each group, there's 4 factorial different permutations. So we're going to divide that out. And so we're going to enter 27 into the calculator, push the math button, the right arrow key to PRB, and then go down to NCR, then enter 4 and enter. So you should have 27 NCR 4 in your calculator, and we get 17,550 well, we could say combinations. We could just say combinations. I don't really care what you call them, but there you go. So if you got that right, excellent. Try number 37, and when you come back, we'll do it together. All right, we're back. So this is going to be C52-5, 52C5. We have 52 options for the first card. We're not allowed to choose a card more than once, so we have 51 for the second choice, 50 for the third choice, 49 options for the fourth choice, and 48 options for the fifth choice. 1, 2, 3, 4, 5. But if you get a poker hand, let's say you get the ace of hearts, and let's say you get the 8 of clubs. I can't really draw that. I don't know what that looks like. And then you get a 5 of diamonds, and then you get the ace of diamonds, and then you get a queen of hearts. So let's say that this is your poker hand. Well, it doesn't make any difference how you order these. If you switch these two, so the 8 is at the left, does that change your poker hand? No, it doesn't change it. It's the same group of cards. It's the same combinations. So we're not counting permutations. We're only counting combinations. So if you find this number here, the product, you're counting all the permutations. So we have to divide out the number of permutations for each group. So how many ways can you permute this? Well, you can permute it 5 factorial times. So of course now we go to the calculator. We enter 52, push the math button, right arrow key to PRB, down to number 3, NCR, enter 5, press enter. So in your calculator you should see 52 NCR 5. Press enter, and then we get 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. So if you got that right, excellent. 2,598,960 hands. Okay, so go ahead and try 38, and when you come back, we'll do it together. Okay, we're back. So this is going to be C. Let's see, candy bar, banana, apple. Let's count these. 1, 2, 3, 4, 5, 6. So there's 6 things. And you're going to choose 3 of them. So this is often called 6 choose 3 to abbreviate that. So you have 6 things to choose from for the first option, but you can't choose again. There's no repetition here. So you have 5 options for the second choice and 4 options for the third choice. So we're choosing 3 things to eat. So we have 1, 2, 3 things. But do permutations matter? If you choose the candy bar, then you choose the banana, then you choose the apple, is that different from choosing the apple first, then the candy bar, then the banana? Is that different? No, it's the same thing. It's the same group of things. So when you calculate this, that's counting the permutations. We don't want the permutations. So we have to divide out the number of permutations. But for one group of 3 things, how many different permutations are there? Well, we already figured that out in the previous problems. It's just 3 factorial permutations. That's the way you can, number of ways you can line up 3 things. Again, lining up is just the same thing as permutations. So, go to our calculator, and we'll enter 6, and then the math button, right arrow key to PRB, down arrow key to NCR, and then enter 3, and then press enter. So what you should see in your calculator is 6 NCR 3. So when you press enter, you should get 20. 20 outcome variations. So if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Screenshot number 1, number 2, number 3, 4, 5, 6, 7, and 8. But don't go before you get the homework. Remember, the homework is not optional. So here's screenshot number 1 of the homework, and number 2, and number 3. And remember, it's not enough just to attempt the homework. It must be done completely and correctly. So you must check all of your answers. And if you get the wrong answer, that means that you go back and you fix it. Don't complete your homework with a bunch of incorrect answers. Homework with incorrect answers is incomplete homework. So get that homework done, and I'll look forward to seeing you in the next class.